The other type of static equilibrium problem that we'll often see involves an object that is connected to a vertical wall by a hinge. So here's our vertical wall. Here's our object. Again, we'll think of this as a long, narrow bar. Connected via a hinge. And we have a cable that is running from the opposite end of the bar to the wall. And let us say this is a 20-degree angle that the cable makes with the horizontal. And we know that the mass of this bar is 40 kilograms. We're told that the bar is in static equilibrium. And we want to find the magnitude of the tension in the cable. And the horizontal and vertical components of the force that the hinge applies to the bar. To see why there must be a force being applied by the hinge, let's look at the other forces that we know are being applied to this bar. And just like in the previous problem, we will assume that the thickness of the bar is small enough that we can safely ignore it. We know that we have the weight of the bar pointing down at its center. We have the tension being applied at that 20-degree angle from the right edge of the bar. We are not given a length of the bar. We're just going to say that the bar has length L. If this was the full story, if this was the complete correct free body diagram for the bar, there would be no way that the bar could be in static equilibrium. No matter what the values of the tension and the weight are, there would have to be a net force to the left. Therefore, we know at the very least the horizontal component of the force from the hinge must point to the right. We can also think in terms of torque. If we imagine the center of the bar as the pivot point, then the gravitational force acting on the bar offers or exerts no torque. The tension would exert a counterclockwise torque. Therefore, the force from the hinge would have to provide a clockwise torque. And so we know that the force from the hinge is going to have to point up and to the right. Again, we know the x component must point to the right for the net force in the x direction to be 0. And then since it must provide a clockwise torque around the center of the bar, the y component must then point upward. Just like we discussed in the last problem, if we have a force that we don't know much about, then we want to make that the pivot point, because that way it exerts no torque when we use the torque net equals 0 equation. So again, to find the magnitude of the tension, without thinking about torque, if we just think about net force in the x or y directions, here the gravitational force is the only one that we have complete information about. There would be no way to solve for the tension without also involving the force from the hinge. So the easiest way to go about it is to say at the pivot point, is at the hinge, so that when we use torque net equals 0, we know again the hinge provides no torque around that pivot point, So we have the gravitational force, which will provide a clockwise or negative torque. It is a distance L over 2 from the hinge. Force equals mg. And that is making, the r vector there is making a 90-degree angle with that force. So we have negative L over 2 mg sine of 90 degrees. The tension is one full length of the bar away from the hinge, so length L. Force is F sub t. The r vector here runs from the left edge to the right edge, and so the angle between that r vector pointing horizontally and the tension is 20 degrees. All of that must equal 0. Sine of 90 equals 1. And notice that we can factor out an L and cancel it. So the fact that we have not been given the length of the bar doesn't matter. And if we solve this for the tension, we have tension times sine 20 equals mg over 2, or the tension equals mg over 2 sine 20 degrees. We know the mass is 40 kilograms. G is 9.8 meters per second squared. And if we plug that all in, we'll get that the magnitude of the tension is 573.1 newtons. From here, we're also looking for the horizontal and vertical components of the force that the hinge applies to the bar. Again, as we discussed earlier, we would expect that those components will point to the right and up. We know mg, we now know the tension, and so probably the most straightforward way to go about this is to use the net force equals 0 equations in the x direction and y direction. We could choose a different pivot point other than the hinge and look for the, again, net torque equals 0. But there are more things that we need to consider there. Using F net equals 0 is probably the simpler way to go. So in the x direction, we have the x component of the force from the hinge pointing to the right, and we have the x component or cosine component of the tension pointing to the left. So we have F of h in the x direction minus tension cosine 20 degrees equals 0, or the x component of the force from the hinge equals F sub t cosine 20, and plugging in the magnitude of the tension that we just found, we would find that the force from the hinge has an x component of 538.5 newtons. Similarly, we can use the fact that the y component of the net force also equals 0. Here we just need to be careful. We do have 3 y components. So we have the y component of the force from the hinge plus F sub t sine 20 minus mg all equals 0. Or solving for the y component of the force from the hinge, we get mg minus ft sine 20. And plugging everything in, we find that the y component of the force from the hinge is 196.0 newtons. If we were asked instead to find the magnitude and direction of the force from the hinge, we would go about it the same way. Having now found the x and y components, we'd use the Pythagorean theorem to find the magnitude of the force and the inverse tangent of the y component over the x component to find the direction that it points in. You'd similarly imagine modifications to the problem. For instance, there could be an additional mass placed somewhere along the bar. Doesn't change conceptually how we go about the problem. It would just be one more force that we need to consider.